Okay, it's lecture 19 of our semester. Okay, let's go to today's topic, small signal analysis. So the lecture progress now arrive at transient device simulation. So now you can simulate the response of your device with respect to certain voltage excitation. So yes, you can do it, but today we will talk about a subcategory of similar transient program. Okay. So now let's think about this one. Since you have already made the code for your transient simulation, now you can simulate any arbitrary voltage excitation. Please consider a single device, a PN junction. We have already simulated this device quite many times with different analysis. So this is a symmetric one with 10 to the 17 per cubic centimeter. So you have done it. Let's say that your cathode is grounded and anode voltage only, the anode voltage is varied. So this is a typical situation, and when anode voltage is positive, we call it as a forward mode operation, and when anode voltage relative to the cathode voltage is negative, then we say that this is in its reverse mode. So anyway, now let's assume that we have applied this waveform. So anode voltage as a function of time contains only two terms in this case. The first term is this term, and second term is time dependent term. Okay, good. However, in this case, we explicitly say that this takes a certain sinusoidal waveform. What does it mean? For example, if we have a time axis and anode voltage, in general, we can, for example, make this kind of waveform. Yes. So, and let's say that, for example, this is 0.5 volt, and we apply 0.0 volt and 1.0 volt. This kind of large difference between a certain level and another level can be possible in general case. However, right now, in this approximation or in this assumption here, so we do not consider this kind of general expression for our waveform. We only consider this one. Consider a certain DC value here, and after that, just to impose additional sinusoidal wave, and its shape is given as this one. So what we can do is just to change the phase, change the frequency of this excitation, and also change amplitude of this excitation. That is possible in this time dependent term. Of course, it is quite obvious that if we have larger amplitude, then we will have this form, and if we have small amplitude, then we will have this form. This is quite easy to understand. And if we have high frequency, then we will have the behavior looks like this, and if we have a low frequency, then we will have the form like this. So this is quite easy to understand. Up to now, yes, this is already quite much restricted. We cannot consider arbitrary waveform. We can just consider just the sum of DC and sinusoidal waveform. It is already quite much restricted. However, here we introduce a further restriction for our voltage. It is the small amplitude is understood. So, for example, typical case, let's say that just 1 millivolt or 1 microvolt, 1 nanovolt, this kind of numbers are regarded as a small enough number. For example, 1 volt, certainly it is not regarded as a small number. Of course, the definition of small is a little bit ambiguous. So, what is small? Is this number is really small or not? So, it is a little bit difficult to say. However, anyway, we can consider two different extremes, small amplitude and large amplitude, and we will consider only small amplitude case in this case. Yes, now we can think about this one. Then now we can, let's try to solve just general transient DD simulation. So what is it? The code you have implemented in your previous homework, then you will get, yes, this current. What you did was actually calculating this anode current, and yes, after some time later, of course, at the beginning of your transient simulation, you will have some different reactions on that. So let me just open it once again. So at the end of our previous lecture, okay, so maybe you remember this one. Here we have a quite high frequency excitation for our PN junction, and that was voltage. In this case, this is anode voltage, and this is, of course, this is sorry. So this is not our PN junction, but that was rectifier. But anyway, this is our input voltage, and this was our output voltage. So please have a look at, although we have implemented or applied just pure sinusoidal waveform, but response shown here, it doesn't show the shape, just looks like a sine or cosine. So you can easily understand, this is not the case of our current interest. Why do we have this kind of behavior? So here, when we have a look at this one, the swing, peak to peak swing was 2 volt. So we are now applying quite a large amplitude sine or signal to this case. In this case, what is the DC voltage? DC voltage is just 0 volt. Then how about the time dependent amplitude? The amplitude is just 1 volt. That's the reason why we have 2 volt peak to peak values. So we are not talking about the case like this. Instead, what we are considering is just applying this one. So quite close to, for example, certain number, and only a little difference from this value. So that was our, that is our current assumed voltage form. So now anyway, so as you have seen it, so at the initial phase of your transient response, so the shape seems to be quite not sinusoidal. But now let's observe the anode current, yes, here, after a long time passed. It means that wait for a while. So although at the initial stage this system can show certain unexpected behavior, but we are not talking about that one. So after some time later, then now still input signal is always given as a periodic signal. So the output of this system will be also sinusoid. Oh, sorry about that. So I have to match the phase. So okay, sorry about that. But anyway, after long time has passed, now if it has the frequency of f in the case of our input signal, then the same frequency will be found in our output signal too. So it is quite natural to understand this behavior. Let's think about a pupil in the elementary school. So he or she was in the kindergarten for a while. So now in Korea, March, so now he or she became a pupil. Okay, wow. Now I'm going to the school, not kindergarten. So now think about the life of this guy. What will happen? At the initial phase, there is a huge difference between kindergarten and school. So maybe getting up earlier and going to there and spend more times in the school and go to a certain private school for additional education. So therefore maybe in March or April there will be certain uncertainty over its behavior, his or her behavior. However, now let's go to May or June. Now everything is just stabilized, and yes, so he or she can wake up early enough and prepare and go to school. After that, every life is stabilized. So quite similarly here, if we have waited sufficiently long time, then we can expect that initial transient effect is all gone, and only we will have the response corresponding to frequency f. That is our assumption. Of course, there is an assumption. This assumption is valid only when we only have small amplitude of Vm. How can we say so? Let's say that our amplitude Vm is not small enough. Then what will happen? If we have quite large amplitude, then even when we have waited for a long time, but eventually what we will get is not just a signal having fundamental frequency omega, but we will find other signals having the multiple of this fundamental signal, because this large signal amplitude introduces some non-linearity in our system, so it can generate multiple frequency indices. So I think that this is quite important. So simply speaking, like this, if your system is operated in small signal mode, then if you have an input whose frequency is just function frequency f, then your output signal will have also the frequency of f. However, if you have a large signal system, then if you have f signal, then you will have multiple signals whose frequency is f, 2 times f, 3 times f, blah blah blah, and multiple of fundamental frequency will be observed. So right now in this small signal analysis, we are assuming that we are currently living in this area, and our small signal system does not introduce any other frequency components, because it can be treated as linear system. So yes, so this one-to-one correspondence of frequencies, input frequencies and output frequency is the property of a linear system. So now this system is called as linearized system. So it sounds a little bit difficult to understand, but let me just explain a little bit further. So now think about your PN junction. Your PN junction can take any arbitrary anode voltage, and it can generate also anode current. So the relation between these two components are nonlinear. However, what I wanted to say is, now let's assume the case we are currently considering. Now we have DC and small amplitude and frequency f. In this case, of course, still our system itself is nonlinear. So if we have a certain input voltage, then it will just take this nonlinear function, and we will have a certain anode response, and it of course contains something and time dependent one. This one is time dependent one, and this one is time dependent one. But when we say a linearized system, we are not talking about this entire system. Yes, it takes the entire V value, and as an output we have an entire current value. But in this linearized PN junction, now input is no longer the entire value. Instead of that, we have just small time dependent term is used as an input voltage, and also only small amount of time varying quantity is considered as t, and of course we have a cosine term due to the phase difference. So now we have this system. Please make a clear distinction between this first original system and this linearized system. the first system is the whole system takes entire voltage and generates entire current. But in this system, we consider just time dependent part only and consider only time dependent one. And in this case, we can say this one is linearized when the amplitude of our input signal is small. Of course, if we have large enough sinusoidal signal, then this linearization is no longer valid, and we must consider the full system. So the first system should be considered. However, under small signal approximation, we can rely on this second linearized system that is explained here. So now let's come back to our original lecture material. Now our anode current can be expressed as the DC current and small signal time dependent current. Due to the phase difference, we can consider sine term and cosine term, but anyway, both of them contribute only frequency F component. Okay, so this question, the answer of this question is quite clear. So now we wanted to this thing. Well, now V amp is so small, so therefore instead of having the value itself, the value of our output current itself, so we can measure so anode current and its a sine component, and anode current its a cosine component. We can always get these values out of our transient simulation. However, it is really related with amplitude. For example, let's say I have used 1 millivolt for V amplitude. Then what will happen? Yes, we will have a certain number and certain number, sine and cosine component. And let's assume that instead of this 1 millivolt, well, I just used 1 microvolt as an amplitude. So what will happen? In this case, the measured or simulated amplitude will be just 1,000 times smaller than that. So actually, the current itself is not important, but what we have to do is the ratio between our small signal anode current and small signal voltage amplitude. We must calculate this ratio. This ratio is important, and of course, you know, since this is current divided by voltage, and this is corresponding to certain admittance parameter, so we can calculate this admittance parameter. Then how can you calculate this admittance parameter? Of course, what we can do is quite simple. Just to run a long enough transient simulation. So why we need long simulation? In order to eliminate the initial transient effect. So now system is fully stabilized. After that, just for one time period, calculate sine and cosine coefficient. You know that since sine and cosine, these functions are orthogonal in a period, so multiplying sine and integrating, then that will give us the sine amplitude, and multiply cosine and take integration, that will give us the cosine coefficient. So it is easy and straightforward to calculate these amplitudes. So it's not that difficult. So let me just show you this example. So now I just consider PN junction, not rectifier itself. I just consider PN junction, PN diode, and 1 megahertz signal is applied. So F is 10 to the 6 hertz. So now amplitude is 1 volt. It means that my V amp is 1 millivolt. After that, I just wait for long time. I mean that 10 period has passed. And what is this 0.5? Means that my DC voltage is 0.5 volt. So simply speaking, within a period, the peak value I applied was 0.501 volt, and the lowest voltage I applied was 0.499 volt. I just applied the small signal just to swing around 0.5 volt, the DC voltage. So please have a look at the shape. This is not voltage, but this is anode current. So anode current, of course, when you have a look at this, just looks like a sinusoidal wave, and maybe somewhere here we have a certain average value. This one is corresponding to this DC value, and this DC value is not provided from our small signal amplitude, not by our 1 megahertz signal, but it was obtained from just DC voltage. We applied 0.5 volt to our system, so 0.5 volt DC voltage generated this average level, and on top of that we have this time dependent one, and this is originated from our small signal amplitude. So if we have, for example, instead of 2 millivolt, let's say that we have 1 millivolt, let's say we have 2 millivolt, then what will happen to our waveform? Our waveform will just look like this, twice scaled by this amplitude. So now we have this form, so quite much expected, and you know, here we have a certain amplitude, and this, from this blue simulation result, we can extract its sine and cosine amplitude, and you can find that okay, this and that are our sine amplitude and cosine amplitude. Please note that we have applied sine, so sine to sine amplitude, this is corresponding to the in phase response, and this component shows that although we have applied sine wave, but we are now getting the cosine wave. So this is out of phase response. So yes, we can calculate this one. Okay, so in order to perform this simulation, please try to estimate the computational effort you have supplied to this system. So first of all, you must prepare 0.5 DC case. It's good. First, get the DC solution at 0.5. After that, you perform transient simulation. So transient simulation with 10 period. So for each period, I just introduce 100 intervals. So it means that we have performed 1000 times solution procedure for this calculation. After that, what we get is, okay, the y parameter, admittance parameter, as a function of frequency omega. Now we have just 1.41 megahertz. Then next question is, okay, now we have 1 megahertz. Then how about 10 megahertz? Now think about what you have to do to calculate the y parameter at 1 megahertz. What you have to do is, once again, yes, this 0.5 volt DC solution can be reused. However, transient simulation should be performed once again with a different frequency. Yes, after that you will have a 10 megahertz response. So for each frequency, actually what we have to do is this long transient simulation. I just skip the one for post-process evaluating the amplitude, because this is much faster than transient simulation. Okay, now let's go to the same situation with much higher frequency. Previously we have just considered 1 megahertz signal, but now we have 100 times higher frequency. And when you have a look at the anode current, how does it look like? Can you still say this is corresponding to a sine wave? So previously, yes, although we have a small difference, small shift, but roughly speaking, this blue line just looks like a sine wave, not cosine wave, because cosine wave starts from non-zero value and sine wave starts from zero value. However, when you have a look at this one, this is clearly corresponding to what? Corresponding to cosine wave. So when we calculate the cosine amplitude, this is the value. So of course sine term is not that high, so quite similar to the previous one. So that's the reason why we have seemingly almost cosine-like behavior of our signal. So simply speaking, yes, even this simple PN junction has a quite dynamic frequency response. When you change your operational frequency or signal frequency, then response of your device is quite much dynamic, and we must accurately calculate it. Yes, so now good. Now let's calculate our y parameter as a function of a frequency. For example, from 1 Hz to 10 gigahertz with spacing of a factor of 10, 1, 10, 100, 1 kilo, 10 kilo, 100 kilo, mega, giga. If we follow this kind of thing, then we will have, starting from the zeros to the, what can I say, 11. So we have to solve at least 12 frequency values for calculating these graphs. Then let's start from the DC solution and run several transient simulations. How large is it? So several means that for each frequency we had to perform about 1000 solutions, and there was, for example, 12 frequencies. If we have just a decade difference between neighboring frequency values, but still we have 12. So the amount of time spent for this calculation is maybe 12 kilo solution procedures. Okay. Wow. Of course, a decade difference between neighboring points is a little bit coarse. So if you wanted to have a better resolution, then you have to have a smaller steps between your neighboring frequency values, so it can easily exceed this number. Well, so in order to calculate this DC calculation, you had to spend your computational effort. So typically, in order to get the solution, the number of Newton iteration or solution procedure is just around of a few or several 10 iterations. However, bias points are required. However, now you have to solve much larger number of solutions procedures to get frequency responses by applying the transient behavior. Okay, this is the general description. Okay, so if we stop here, then maybe you think that this small signal analysis is almost impossible, because in many cases DC simulation itself is computationally heavy. However, it means that in order to perform any kind of small signal analysis, we have to spend orders of magnitude more efforts, computational efforts, to this system. This is not affordable in many practical cases. So today I will talk about an efficient approach. So this is really important. So the idea is, can we avoid the time-consuming transient calculation to obtain frequency response, so sorry about this typo, efficiently? And the answer is, fortunately, yes, we can reduce the computational burden to calculate the Y parameter drastically. So now in this efficient approach, this is the computational burden. Single DC calculation, this is the same as before, and a factor of number of frequencies, this is the same as before, but real breakthrough comes from this part. What is it? This is now, in order to calculate Y parameter at a given frequency, it can be done much faster. So previously, please remember that we need around 1000 solutions to calculate a single frequency response, but in this new approach, this one is just one-shot calculation. One shot means that when we say 1000 solution procedure, what does it mean? Actually, it means that we have to solve 1000 bias points, and 1000 bias points means that each bias we need multiple Newton iterations. So if we consider the total number of matrix solution AX equal to B, that will be more than this number. However, this one-shot solution means that we just solve this AX equal to B, so the system only once. So let's say that for each bias point, in average we need 3 Newton iterations. Then we need 3000 times solution to get one frequency response. And now in this case, we need only one solution or one linear system solution just like corresponding to 1 Newton iteration. So the difference would be orders of 1,000, thousands times faster than before. This is the real breakthrough. Of course, please note that so I'm not cheating at all, and the magic comes from what? The magic comes from our assumption, small amplitude. Without this small amplitude, our great enhancement in efficiency cannot be achieved. So please note that there is no free lunch. This is obtained with sacrificing the generality of our calculation. However, fortunately, our parameter of interest, this y parameter, by its own definition, it always assumes the smallness of input parameter, input voltage excitation. So it is completely okay to assuming this small input voltage excitation. Okay, so I hope that now you are fully motivated about the huge computational benefit by this one-shot approach. Then how can you obtain the y parameters quite efficiently without performing the long time transient? It is simply given by this way. So our unknown variables are expressed as this form. So here we have phi and p, they are solution variables, and now we assume that yes, it has this term and time dependent term. Time varying terms are regarded as once again small, as shown here. Why we can say it is small? Because this is the system were quite passive. So if we apply small voltage excitation, then we assume that the response will be also quite small. So I have to say that not all systems behave like this. If you have a little difference in your input, sometimes it can make quite a big difference. Let's think about a bridge here. Here we have a bridge, and it looks completely okay before it cracks. However, if our bridge system is close to its end, its lifetime, then maybe adding one more small box in this bridge will eventually make a certain crack of the entire system. Sometimes it is not easy to say when small input is applied, always the response is small. So it is not the case. Or please think about this one. Now we have this kind of thing. Here we have so many load and so many load. So like this is 1 ton and this is 1 ton. And say that here we have, for example, a small amount, 1 kilogram is added. So that's the reason why this seesaw is placed in that one. So now let's just add small box whose weight is just or mass is just 2 kilogram. Then what will happen if we add this one, small, relatively small, but that will break this system, and this system will become just located completely the opposite phase. So I mean that we are now currently assuming that since input is small, the output will be also small. That is our assumption, but please be careful. Sometimes it's not the truth. So sometimes we have a certain very critical system, small difference in its input can introduce huge difference in its output. So, however, fortunately, in many cases, our system is not that sensitive to input value, so we can just linear response of our responses. So now we say that these are large numbers and these are small numbers, and under this assumption we can write the drift diffusion equation in this way. Well, although it looks a little bit complicated, but please note that this is nothing but the electric field or a displacement vector with a negative sign, and although it looks quite complicated, it is just electron current density vector, and this is a whole current density vector. And yes, this is nothing but just hole density. This is electron density. So I just made a double counting of one single term, separating it into two terms like DC and small signal terms. Well, once after we do it, okay, here I just summarize its current density, what exactly the current density looks like. So starting from our original form, we can just introduce terms. So here we have electron density and potential. So please insert NDC and delta N, and please insert phi DC and delta phi, and just to play with those terms. You can easily understand there will be 4 different terms out of this calculation, but please note that here we have just 2 terms. Starting from this drift term, we may expect 4 different terms. However, DC coupled with this DC term is just considered not in this time varying current density, but it is considered in our DC term. So we don't have to worry about it. And how about remaining 3 terms? Yes, 2 of them are shown here. Then why we have 1 missing term? It is because it was obtained from what? Here, combination of delta N and delta phi. We have already assumed that delta N is small and delta phi is small, and multiplying them will give us extremely small value. And usually in our treatment, we consider that second order term of small variables can be safely neglected under the approximation of smallness of our variables. So that's the reason why here we don't have terms like delta n gradient delta phi. Of course we have it, but we neglect this one under smallness of approximation. Yes, you can do it quite similarly. But maybe you feel some similarity with our derivation right now and our previous study. Do you remember the procedure we have used similar approximations? So when we consider Newton-Raphson method, so we assume that corrections or update of our solution variable small. So therefore, second order term or higher order terms are all neglected, and we took only linear term in the form of a Jacobian matrix. So quite similarly, we are now doing same thing. Linear approximation is applied to our quantities, and yes, we are doing this job. So now, so once again, this is the entire system. So it contains both of DC term and small signal terms. Both of them are considered in this case. However, let's consider only DC term. When you have a look at these three terms, actually the black colored terms are corresponding to our DC simulation. When we simulate the DC problem, then we consider only these black colored terms and get the DC solution. So are you with me? So please note that, for example, divergence of J and DC itself is 0 even without our additional small signal excitation. So simply means that this one can be eliminated. Also this term can be eliminated. And please note that this black colored one here and here and here, this is DC Poisson equation, and also DC Poisson equation is satisfied by our DC solutions. So entirely all of these terms can be eliminated. I'm not saying that Q and dot is 0. Individual term is not 0 at all. However, their summation is 0 because they are satisfying the DC Poisson equation. So simply speaking, yes, we can make a system for delta quantities. We can generate a system whose variables are only small signal responses. So now we can have this form. Well, so now you can understand. Simply speaking, without this delta sign, the system looks exactly same as before. So we just introduced delta sign to this system. So if we have, but please don't be confused with the original system and this system for delta quantities, small signal quantities. So let me just explain about its relation to the Jacobian. The linearized system, where unknown variables are written with delta values, is closely related to the Jacobian matrix. So in its left hand side, we can find these quantities, and all of these quantities are corresponding to the Jacobian component. So simply speaking, the DC Jacobian matrix is related to the small signal analysis at zero frequency. Why I'm saying zero frequency? Because here we have time dependent terms here, but in our DC Jacobian we don't care about the time dependence. So these parts are corresponding to the DC Jacobian matrix. So simply speaking, if we wanted to consider the small signal response at zero frequency, what we can do is just to reuse your Jacobian matrix. So of course, in the case of non-zero frequency, we have to consider this time dependent terms. However, it is not that difficult because here we have terms like partial derivative with respect to the time, and in this phase notation, so we can simply add j omega to get the phase expression for our time derivative operator. So in the frequency domain, we can simply write down in this way. This is of course j times omega here, and that is corresponding to our time derivative operator, and this is the one we have to solve. So in the case of a non-zero frequency, well, we are now introducing this pure imaginary number unit j. So j is defined as just square root of -1. So now in this non-zero frequency, actually the system we have to consider now contains complex numbers in its entry. So I mean that we are not no longer solving 1 1 0 0. This is not we are solving right now with non-zero frequency. Now we have to solve, for example, 1 plus j and 1 minus j, something like that. Our entries can be a complex number in general. Of course, complex number not appearing anywhere, arbitrary position, but only occurs at certain points with diagonal path for electron continuity and hole continuity. But anyway, we must consider these terms. Okay. So okay, now let's try to calculate the y parameter. So how can you calculate this y parameter? First, prepare the DC solution. For example, if we wanted to consider 0.5 volt, then first of all we must ramp up our anode voltage up to 0.5 volt. So now we have increased it. So now, yes, this is just a typical one. So just I will assume that you can do it. Then please reuse your Jacobian matrix. So now you can have the Jacobian matrix already made, and after that just to impose boundary condition. So you can apply this new boundary condition like this one. Delta phi at anode equal to 1. Why we have 1? This 1 is no longer corresponding to 1 volt, just a unit number. So since this is 1, every response is just normalized to this 1. So we will have just a simple y parameter out of current value. Okay, so please try to solve it. Okay, let me just give you an example. This is just the same PN junction we have considered up to now. We have 10 to the 17 per cubic centimeter for its anode region and cathode region, and once again bias it to 0.5 volt, and when you apply additional small voltage to your here, this right position, this is anode, then it will have additional 1 volt. Because you have applied quite a small 1 volt, small 1 volt seems to be quite ironic. So it is this number, since you have, for example, applied 0.01 volt, 1 millivolt, then it will corresponding to 1 millivolt. This number 1 means that the ratio between them is 1. So if you apply small voltage excitation to your right hand side or another contact, then it means that for this reason, what is it? This is corresponding to your p-type reason, then potential is almost the same. And now you can see that in your junction you have most of voltage difference because your cathode part does not change its potential. So what doesn't mean is when you apply your potential or apply the voltage a little bit, then that additional voltage will be just applied to your depletion reason. That is shown here. Okay. So of course you can not only the potential but also other quantities like carrier densities can be calculated by this way. So we are now looking at the shape of our quantities. Okay. So what does it mean here? Can you explain what does it mean? So since we are now applying additional voltage to our forward biased PN junction, so if our PN junction is further highly biased, then we expect that the reduction of our depletion layer. Then what does it mean is this part is p-type region, and here we have increase of hole, I'm not quite sure. Yes, increase. It means that this is corresponding to, maybe this is corresponding to the hole density, and this is corresponding to the electron density. So means that now we have previous depletion layer is now reduced because we have applied further bias points. Okay. Please note that here, although it looks like just one single line, but each of this blue curve and red curve actually contains two different contents. One is here we have a symbol, and here we have a line. This line is obtained from small signal frequency domain calculation, and this symbol is obtained from our long transient simulation. So you can see that the agreement is quite good. It is because, you know, I have used two different values like 0.5 and 0.501, so just 1 millivolt excitation voltage. So it looks quite okay for this case. And of course we can calculate the terminal current. So please be careful. Calculation of a terminal current is a little bit tricky, so please don't make any mistakes. And now when you go to non-zero frequency, now we have to add these complex numbers in our system matrix, and also in this case displacement current should be calculated with care. You know, displacement current, it has the form of like a time derivative of this displacement vector. So now it becomes j omega times delta d vector. So we must calculate this one. So out of your solution variable, then please try to calculate this one. If you make any mistakes, then there will be some problems satisfying the current conservation between your anode contact and cathode contact. So now I assume that you can calculate all of these kind of things. Then please try to calculate your responses. So if you have a low frequency and high frequency, then you will have quite much different behavior. For example, can you make a comparison between these two cases? One case was 1 megahertz and one case is 100 megahertz. And when you have a look at this blue curve corresponding to the electrostatic potential, then it looks like so actually, sorry about that. The real part of your electrostatic potential, real part 1, and imaginary part 1, that is shown in this lead case. And when you have a look at this one, yes, it has just values of 10 to the minus 6. And when you have a look at this one, this seems like a much larger value. So please, 100 times higher values are obtained for this imaginary part. Then why do we have a larger imaginary part? It is quite simple, because here we have the terms corresponding to F. Previously it was 1 megahertz and now it becomes 100 megahertz. So the matrix, our system matrix, has 100 times higher values for its imaginary part. So that's the reason why we have higher responses. So now if you can calculate these quantities, now you can sweep your frequency and calculate your real part and imaginary part of anode current. So now you can see that. So this real part shows almost no dependencies in its frequency term. However, this imaginary part term is rapidly increasing, almost linearly increasing with our frequency. So you can treat it in this way. R and this is the model for our PN junction. So if we have low frequency, then what will happen? This at low frequency, actually this capacitance cannot conduct any current, and we will see just the real part. So this real part is corresponding to this value, and yes, our Y parameter, its real part is just corresponding to the inverse of our R. However, if we go to higher and higher frequency, then this capacitor will provide additional admittance corresponding to J omega C. And this J omega C is calculated from these graphs. So what people do is, with this ticket simulator, is just to make a certain structure whose DC characteristics is well matched. After that, apply it to the small signal analysis and extract certain Y parameters, And in order to match these y parameters, introduce a small signal model like this one for simple case, and try to match or try to find out some parameters like R or C to match expected behavior of our circuit. So this is used to match our device characteristics in the RF frequency range with compact model. So we must perform some effort on this one. Okay, so now let me just summarize today's talk. I think that today's talk is quite much important in practice. If you are working with RF characterization, actually this is really important. Although in general, everything can be done with general transient simulation, but in many cases we are more interested with frequency dependent responses. In this case, we can introduce really huge enhancement of our computational efficiency by introducing this kind of frequency domain analysis. Of course, it has its own restriction. Small amplitude must be assumed in order to get this one. However, in many applications, we can, without any big problems, we can introduce a small approximation about the amplitude. So it is quite good to have this kind of approximation. So this is really important in practice. So your homework is please try to implement a small signal DD solver. So what you have to do is just once after you have the converged solution, and take that DC Jacobian and add the diagonal term for current continuity equations and solve that problem with proper boundary conditions. Please check a valid range of a small signal approximation. Means that just to increase your amplitude. Small signal approximation cannot actually change the amplitude. What I'm saying is, how can we check the validity of a small signal approximation? Please learn many transient simulations with different amplitudes. Then if you have a large amplitude, then your observed response, current response, will deviate from the one expected by small signal DD solver. So anyway, please try to implement your own small signal DD solver. This is quite important, and once you can understand this technique, then actually you can apply it to other types of analysis like green function. And if you can apply this green function technique, then you can use it for noise simulation and also variability analysis. These are quite important in practice for efficient simulation of important problems. Okay, so I would like to wrap up today's lecture now, and please make some effort to understand this one. Please note that my final comment is, although I'm saying that this j omega delta n, something like that, it is not integrated. Please be careful. Your continuity equations are not or not their original form, but you have integrated over the control volume. So even in this time dependent term or time derivative term, you must take integration over the control volume. Otherwise, you will get huge difference in calculate quantity, because you know your control volume is more or less the length of 10 to the 9 meter, so you must multiply that number into it, otherwise effectively it exaggerate your frequency and you will find quite a bad result out of your simulation. Okay, that was my final caution.